Hello everyone. I am Shelly, marketing head at MoogleLabs, and it is with great pleasure that we host you today for the Transformers Basics to Implementation webinar with Vaibhav Kumar, the senior ML engineer at MoogleLabs. I will take a few minutes to explain the format for today's webinar. Firstly, Vaibhav will give a presentation while explaining the concept of transformers in machine learning and take you through the basics before explaining its implementation. The webinar will take around 30 to 45 minutes. Then all the participants can take some time to ask industry specific questions. Please feel free to add your questions to the chat as they arise. Vaibhav can address them at the end. Also, if you can please keep your screens on to see the presentation as the speakers go through various points. Now, our extremely sincere and knowledgeable ML expert, please take over the screen.
Thank you, Minkle. Hello, everyone. I am Vaibhav, and I am ML expert with CSCA Labs, with Moogle Labs here at CSCA Infotech. And I am basically mainly primary working on NLP problems. So transformers are basically leading to the cutting edge state of the art technology in the field of NLP, natural language processing. So we'll take a look at how uh, we are using transformers, in what applications we are using it, and how from its basics, like from RNNs to journey to encoder decoder models to transformers, and how state of the art models are actually present day state of the art models are uh, working today. So we'll have a journey through that. Let me start with that. So as we all know, to process sequential input data, the traditional and neural networks does not work well. So we had always had some special type of neural networks called RNNs, or recurrent neural networks, which primarily focused on applications towards tasks like translation, text summarization, or other kind of sequential data. The sequential data means where there is a sequence to the information is in a sequence, and the sequence is there in terms of time, in terms of its positioning. So like in text, there is no time, but there is some positioning of the words. Like in a sentence, I am a student. For example, there is a sequence to words like I comes before am, and then student. So there is a sequence to everything. So that means it is a sequential type of data. So it cannot be it can be the better approach to tackle such problem sequential data is RNNs, or recurrent neural network. What it takes each input at a time, and then takes a next step in a time sequence, and we'll look at that in the coming slides. Then LSTMs are special types of RNNs, which has a different architecture. They are mainly based on RNNs, but they have different kind of um, structure, architecture, and improvement to that is GRUs, which are currently state of the art. LSTM and GRU are state of the art, and has been used in many tasks, like for whether it is stock prediction models, that is sensors data that we currently have. Um, it is all kind of audio signals to even LSTMs has been used in certain vision tasks as well. So for audio and for an NLP task, it is widely used, and its applications for LSTM's applications like encoder decoder models, or so they are used in that way. So examples can be for text task and translation, text summarization. Similar applications are there. We'll look at the applications at the end of the presentation. Uh, then we have this RNN and LSTM, how they work, what are the architectures. I'll guide you through that step by step. So here, this the first in the left corner, we have this. This is a LSTM unit. This is called an LSTM unit, where this XI or XT is the input at time step T, which is giving as input, and this is a loop kind of thing, which is actually it is this same unit is looping in time and giving us output as well. So this loop is actually giving this output, and this is going fed to the next time at the next time step to the same. So this is actually, this is a loop structure, and this can be unrolled in time and can be viewed as like this. So this is unrolled in time means, suppose this is our first input, which can be which is already tokenized and vectorized, like many types of whatever pre-processing is needed to convert this text information to vector is already performed. Like first for text, and suppose we are dealing with a text sentence, I am a student, then we'll need to convert it to into a vector that machine understand, or the computer or uh, mathematical model understands into numbers. So for that, we'll convert this I am a student from using tokens. So that first is tokenization. So tokens are when, and using these tokens with the help of word embeddings, we can generate vectors, right? So then these vectors are fed through these LSTM units in time, same LSTM unit in different stages in time. So this is given to this first at the first time step, it is given as input here, then it generates some output. Suppose it is the output, and this here it is passing its hidden state, means it is kind of some sequence information that it has learned from this time step. It is learning sequence information which is passed to the next time step, and then it is again passed to the next step similarly. But continuously we are also giving it inputs in the form of x0, x1, x2 till last time step, and continuously we are also getting h0, h1, h2 as the outputs. So basically these RNNs for tasks like speech recognition, language modeling, where we can generate we can understand the language and generate text, or language modeling is actually also has number of applications. You can use language models. Then translation applications, text summarization, image captioning. These are some applications that RNNs were used, and they perform pretty well. But the improvement over RNNs were LSTMs. So LSTMs were had a uh, different kind of architecture, or improved kind of architecture, and then they were used and gave better results than RNNs. So LSTMs are actually a special kind of RNNs which have a different kind of architecture, and what the best part is that RNNs do not have long-term dependencies, although they retain some information about the sequence. But when it comes to problems like, suppose I am a student is a short sentence, but if it goes like five to even 5 to 7, more than 5 to 7 vectors are the inputs are there, length of the sequence is more than 5 to 7, then it does not retain that much information because of mainly problems like vanishing gradient or exploding gradient. So such problems, because of such problems, RNNs do not perform well with long-term sequences and long-term dependencies. They do not retain that information over long term. So that's why it LSTMs have a special kind of procedure here, a gate that we'll see in coming slide in coming. So there are three kinds. As we can see, this is similar to below one is the LSTM unit, where there is an input vector is given here, and output is taken at ht minus one, ht plus one, means there are three instances of time. So there are three instances of time, and at every step there is an input given and an output is taken from h2. And the architecture is mentioned in between cell that I'll describe now. But the input is taken, and from the previous there is a cell state, which is the this upper arrow, as you can see in the image in the right hand corner. The upper arrow on the left hand side is actually in we are giving cell state to this, and in the lower one, we are actually giving the output of the previous cell. This is the output of the previous cell, and upper one is the cell state. So this is the cell state that goes through this LSTM unit, which means whatever it has learned previously, it is it is actually passing to the next cell, next time step, not cell, it is passing to the next time step. So the input, the information or the long-term dependency that it has learned over time, it is actually passing it over to the next time step. Similarly, the output is like in this one also, in the upper RNN diagram also, there is a hidden state is passed through, or the information long-term dependency that is passed through. Similarly, here, sorry, here is also same hidden state is passed. And then this xt is also given here. Then this output, this is actually output. So this output is concatenated here. This you can see these two are merging from xt and the previous cell output. These are merging. Merging means there is a concatenation is happening here, and the two vectors are concatenated to grab a bigger bigger vector. So then this concatenated vector is passed through the sigmoid units, and this unit is actually, this is known as forget gate. Means how much this model should forget, how much information it should forget. And this is retaining, it is multiplied here with the previous cell state, and it can forget or learn or whatever information it has. So if suppose, if the output is, if the if through sigmoid unit we are getting 1 as input, so then it works as identity, and the whole state, whatever the previous state was, it is already transferred to the next step. Otherwise, if it is 0, then it means that this cell now should forget everything about previous one. Or if there is a value in between, then it can learn based on that. So this is the forget gate, means how much the model should forget. Then there is an input gate. The middle one is the input gate, where there is a sigmoid unit and there is a 10H unit, where these this concatenated vector that we generated in the first step, that is actually given to both these, to the sigmoid and 10H. And what it represents, the sigmoid unit is actually taking care of what should be updated. Input means what needs to be updated given the input. The next, since we have this input at xt, this input, how much the model should learn, how much the model should improve, it should change its state. So that state change or the learning is actually incorporated through these two, this whole system, where this sigmoid is actually deciding what should be updated, which ones should be updated, and 10H deciding what should be updated. And these are multiplied, means matrix multiplication here, and then cell state is added to this, and then it is passed for the next gate, which is our output gate. Where output gate is also again the same procedure is happening here, where the xt is going through here, and which is passing through sigmoid to what should be updated. And this sigmoid unit will have some weights. All these sigmoid units and edge unit will have some weights, but that is what we are learning here. The model is learning these weights which are related, which are actually related to these sigmoid and 10H units, and then it is passed to this, from the above. There is some cell state and concatenation of the input is given to this 10H on the right. This 10H that you are looking at in the oval shape, that it is giving to this point, and then through this 10H, what should be updated uh, is also given, how much should be updated, and then these are multiplied and given as the output here. So this is like how much long-term dependency is kept. This information is passed through every unit, every time step, and is learned by the model. These weights are learned. That's what main primary task of our machine learning model is. So here output is also taken at every time step, which is actually what we always had in the RNN structure. So this is how LSTMs work. Now, based on these LSTM, some ingenious methods or transformer, similar systems to transformer were already developed, like encoder decoder models, where some where long-term dependencies were used and LSTMs were used for for these tasks, and they performed considerably well over only RNN cells. So these are the encoder decoder models. Let me give you a brief about it, and so that a brief overview, and then we'll go into deep into it. So this is the encoder part here. You can see on the right, there is upper in the upper image, there is an encoder part, which is this is encoder and this is decoder. This is encoder stack means there are number of encoders, and this is decoder stack means there is number of decoders. Here we are taking example of French to English translation, where input is use is étudiant and this output is I am a student is taken. So this is an like black box approach, or you can see this is like a bigger picture of encoder decoder model. For this, every encoder and decoder, if we see on the left, there is an image where this there is a sequence of like LSTM like structure is there, where the same unit is behaving like a encoder and a decoder. So for example, we are giving W, which is actually a starting word, which is actually a starting token or vector, starting token. Special kind of tokens are considered here, so that where to start, where to what should be given. So this W is given as the first input. Then there is X by Z means there are these are words or the sequence of information in time, which is given X, then Y, then Z, one step at a time. Then these steps are, this is the hidden state. You as you can see, hidden states are passed that are through. First it learns X, then it passes its context to Y, then it learns Y, and then pass the whole context to Z. Then this is whole means the whole sequence information is learned through W, X, Y, and Z, and this information is passed to this next cell, which is receiving a new special type of token, which is end of sentence EOS. When this EOS comes, then it can start either generating the output or it can start learning more words. So it can do both things. But here in this example, we are taking that it is starting now to generate the output. So here we are here it is this is W here that we are getting is actually a context vector. What context vector has? It has all the sequence information that it has learned over time in the previous sessions. So then this this W is actually passed through the next time step. This W here that we are getting from US is passed through here, and then it outputs X. Then this X is passed to the next time step, then it generates Y. And similar fashion, if we look at Y is passed and Z is obtained and Z is passed, then end of sentence. So this means this given this sequence of information, we can generate this sequence of information, which is actually on the right. You can see this sequence of information is passed and then similar sequence of information is passed. So encoders are not used as a single unit. They can be used, but they won't give better, they were not giving better results. So the many with experimentation, it was found that a stack of encoders and decoders were more useful in such sequences. So so encoder, encoder basically is doing is actually generating a context vector, is actually learning the behavior over the sequence, over the time, and is actually generating a context vector which can be used to decode it to extract any kind of information, which we'll see later also, that any type of application, but the initial phase is same. The transformer is same, but we can use it for number of applications. So we are actually generating a vector here, and then that vector can be used for multiple tasks like sequence to sequence models, machine translation task, image captioning. Here I have also image captioning example here also, where this is a CNN model, which where the CNN model is learning through this image. These are three you can see. So these are three channels, and based on basic CNN thing, and the CNN actually learns the vector. This is the vector that I'm talking about. It's like a context vector, similar to context vector, not exactly a context vector, similar to context vector, because it has all the features, all the information about this. This is 2D information, right? This is convoluted information that is extracted and put into the form of vector, which is actually this final here. Then this context vector or the final vector is fed to this model, which is LSTM, which has LSTM units here. And then this LSTM units, they are passed through a start. start token here, and that generates some straw. Then it is passing some hidden state to this. Then straw is generating hat, and similarly hat is generating, and this way this whole system is generating the caption for this image, right? So then we'll look at encoder decoder models. Attention mechanism. So this was encoder decoder model. Now we'll look at attention mechanism. What is attention is, how it works and all. So for this is actually different from LSTM or RNN. How? Why was the need for attention? Let me clarify first. Because attentions were good at keeping long-term sequences, but they were not very good at keeping a lot. Means suppose there is an example where in the initial state it is mentioned that Chandigarh is a city, and then somewhere later in the third or fourth line it is used, Chandigarh is used, then it should be inferred that Chandigarh is a city. So it is, this kind of behavior was not possible in text in respect to LSTM units. They had some kind of sequence information, they had some kind of things, but the total attention was not provided to each and every word. Like we humans have attention to things like there is a word like I am a student. Then there we are giving a specific student attention to words like I and a student, but not much giving attention to um, am and a. So it means I and student are needed more attention. And in respect to that, when there is attention given to for translation task, suppose there is if there is a translation task, then I should be converted properly, or it should have more weight corresponding to to the same word like मैं in Hindi. So it should match to the attention should be given more to I in respect if I am generating मैं. Uh, right. So in this sense, so attention is actually this left one here is a single attention unit, and then it can be extrapolated to this multi-head attention layer, which is actually extension to this, and it is actually used in the transformer model. So attention was came before transformers, because it was the concept that the transformers were mainly built on. So attention came a year or two back before. So the main fundamental of attention was that this query QKV, these are three vectors which has the same dimension, and these three vectors are actually Q means the queries or output. Like in the encoder model we were giving, yeah, in the encoder model, since we are giving this W here, W is given here, then it generates something and passes through it. This model here is generating key and values here in the attention mechanism, not here. In the attention mechanism, this is because it is similar to that. In terms of architecture, there are some similarities. So it is generating keys and values, and here it is actually giving some queries. The input given is called queries, and then this is sorry this is keys and values, right? So this Q, K, and V are given through this, and so this is simple multiplication. Here you can see in the formula also that Q and K are multiplied and then scaled through root decay, because of the, if the vector gets large, then there are some problems like a lot of multiplication, and also it might lead to some bigger numbers. So there is scaling is done in this here. So this is the root decays as a scaling factor is used, and then this whole is multiplied with a v vector. There is a softmax layer also, which is actually generating some linear outputs, and then this is multiplied with this v vector, which is actually the formula for the attention model. The same attention model is actually used in the multi-head attention, where this is this is this every vector is passed through linear heads, and so that it can be used. This can be used over a series of. It's not a single, like in encoder also we had a single, and like multi-head attention also. Suppose we do not want to be very specific to a particular word, but we want to make it a general, like I can be, I am a student, or she is a good student. In both things, she is referring to good and as well as student, both. So like this attention should be given to both good and student. So there, in this fashion, so this attention is divided by using multi-head attention. So multi-head means their attention can be given to multiple entities, multiple things, multiple vectors. So this is used as a multi-head attention, right? So then the output is also output from each every this output is same is here. What output we are getting from this scale dot product in a single unit, the same output is received from here, and then it is concatenated. The whole structure here same remains same. The scale dot product, this whole unit is same here, scale dot product. Only the addition is here is linear units, and then concatenation over it, and then a linear layer is also applied here to get the single output. Then to understand the how the context vector works and how the attention works, here is a very good diagram where if you see that I am giving input, I am a student, and then a special token, which means end of sentence, and then it generates some output, right? So that since it is learning phase, consider this as a learning phase. The first sentence is given, and then with the space, with the end of sentence or with a special token, then we are giving it the next sentence because it is learning right now. So how it generates? This attention weights are generating here. These are actually learned through the model attention weights, and they have a special they have a formula based on that it learns. So because it was too mathematical, so I haven't included the, because I wanted to give you a brief. So from here, this, since it is given, then Ye is actually attending to each of the words here. I am a student, and by attending mean there is a particular weight is given to everyone. I is given more weight because there is Ye. It is here. This output is here is A. So it is giving more weight to that because I is more related to A. So it has learned over time that this weight should be given to this as per this attention vector. Then similarly, M is given less weight, is given less weight. So comparatively, we can find the weights here. Similarly, for US, we can find that the weight will be given to M, more weight will be for M. And similarly, for a student, the more weight will be available on the etudiant. Now, this context vector that we have learned, this context vector, that the sequence information that we have learned, this context vector is multiplied uh, through this attention weights, and then output is generated through that, right? So here is an example of this. Suppose, yeah, as you can see on the right, there is a encoder hidden state. So these are hidden states that we are passing. Hidden states mean these every single one of them, they are passing some hidden state through that, right? We are talking that since Rn and that hidden states are passed. These are hidden states that are passed. H1, H2, H3 are three actually different units, and then these three are given these weights. Every unit is these are the weights given here, and scores the weights, and then these are actually weights are uh, normalized, and then it is used to multiply this hidden states with these weights, and multiply each vector with these scores, and then we can generate the context vector for each. So this is whole process of generating the context. How do we are generating? We are getting hidden states. From that hidden states we are getting uh, we already have learned the weights, and then from those weights we multiply the hidden state, then we get the context vector, which is used as a which is used to predict the outputs, right? Next. So what happens after the context vector learns these all these things? So the context vector actually uh, means how attention is looked at, how we are looking at attention. Here, this is an example of self attention. Self attention means in the same sentence, how it is, what kind of words, or how what sequences, um, what information it has learned through that, right? So suppose it is a mapping only. It is only for representational purposes, but it is very good image. So like the is referring is the it here in the right hand side is referring to actually the animal, because if you look at the whole sentence, the animal didn't cross the street because it was too tired. If we are talking about it, if we in a human sense, if we learn about languages, then it here is referring to this animal. Here we know that by our understanding how the model is learning that it is referring to that animal. So the weights here will be my high. So because of the weights, as per the weights is given, there is a the color is more dark. Darker here means higher weights, and then shallower means lower weights. So in this sense, it is referring to the animal. And then similarly for every word here, the and every word will have some context for every word, right? The will also this map here will be for every single word, which is the part of self attention. In the similar fashion, if this on the left hand side, suppose we have a French sentence, and on the right hand side there is a English sentence, then this mapping will also be done in the same manner. So I haven't shown that because this will be same, only the entities will be different, but the mapping will be same, that what is having more attention, what is what the model have learned more, right, in that manner. Next, this is the architecture of the this is the most important part, and this is the architecture of the transformer, where the input is given from here, like input that we were giving in the encoder decoder model everywhere. That input means that every vector is given here. Then it is embeddings means vector generation, tokenization, vector word embeddings to generate the vectors. Then input is given here, and then this positional encoding. Since we are only learning this, we have learned about attention, but we haven't learned about the sequence information. Everything does not have a sequence. We do not have actual position or sequence information where the word the comes before animal. We do not have that. We have what we have more is from that attention vector or context vector. We have learned that what should be given more weightage, what should be given more attention, but we have learned the position or the sequence information. That sequence information is learned through this positional encoding, and then both are added, not concatenated. Here these are added, and it is passed through multi-head attention, and then normalization layer, which is given to the feed forward network, and then again normalize. So every these are two sublayers, feed forward sublayer, and there is a multi-head attention sublayer. So both these layers sublayers are actually normalized as well. And there is a, you can see this is the residual connection as well. Here means whatever we are getting from previous, that is also kept, and whatever this multi-head attention is giving us, that is also kept. Means the learning and the original both are kept and normalized and similar fashion in the feed forward. And so now this NX here, at the input encoder, means the encoder part, the NX here is not one single unit. This is a stack of similar units, like we saw in the encoder diagram also. And that this is not, this is single encoder, but it is stacked up. Like the output from this second add and norm, the feed forward add and norm, is given to the next layer, like input, right? Not input through this multi-head attention. It is given to multi-head attention, because this input and position encoder are done only once, and then through this this part here, from here it is given from here. So it is actually given to this, then this, and in the last, the final encoder light. Suppose we have 6 encoders. From the sixth encoder, we find this and this output, and this is given to this encoder decoder attention. So there are three kinds of encoder decoders. Sorry, yeah, encoder decoder attention. This is the self attention, self attention. Okay. Then this is encoder decoder attention, then output attention. So there are three units here. Similar fashion, outputs is vectorized, and position encoding is performed out, and word embedding and tokenization, everything is performed and then vectorized and then given to this masked multi-head attention layer, which is again masked means, because what why we need masked here is because in case of input, we have access to the whole sentence. So if we are looking at, suppose, it here or because here, then we have, it should learn about whole this everything that is around it. But whatever is passed, whatever will come in the future. So it should know about everything, but in the object in the prediction state, if it learns, then it is not good for the model. So it is actually masked. Only the previous one, that output that already been generated, only those should be kept, and otherwise it is masked. So then this again, this is also passed through residual connection, and normalization is performed here. Then this is passed through multi-head attention layer here, which where this is called the encoder decoder attention, where we are getting inputs from input layer or the encoder, and input from this output embedding or the word vector that we are supposed to uh, give as as a input to generate some output. So this is multi-head attention here, and then add same feed forward network, then linear and softmax. So you can perform any kind of task here. Similar, this NX is also given on the right side, because the same number of decoder models you can have. So this similar fashion, like here, this output is given to multiple encoder decoder units, and in the end, after the sixth or seventh or whatever number, 12th, this is given to this and linear layer, and then to the software layer, where probabilities are actually defined. So based on the probabilities, you can generate the actual text or whatever task is. If it is a classification task, then you can have such a softmax layer. With these last two lines, like last two layers, softmax and linear layers, you can perform your task specific jobs here. So whatever you want to achieve, you can apply that model here. So and then get the output. So it is actually whatever we are learning from the model is part of this, and then the application part is here. So mainly what BERT is also doing is also actually training on this part here only, and applying different kinds of applications in the end. Okay, so for BERT is actually that we are looking for, but is a special kind of transformer developed by Google Research. And so BERT is bidirectional encoder representation from transformers. So I'll come to that. But it is trained on multilingual natural language inference, question pair data set. These are the data sets. MNLI is a data set, QQP is a data set, squared is a data set, and you can see here on the right hand side with A, QQP, QNLI, STS, MRP, CRT, SWAP. These are all the um, data sets and different kind of problems that people have been working on, and the but is being trained and specialized, specially used for applications such as these. So why bidirectional encoder? So actually, BERT is an encoder only stack. Uh, Means we were looking at the end of the day, what we are learning is the learning the what the model knows, what the sequence information was, what uh, what information does the training data had. So that we are learning that finally we are generating a vector. That vector we are generating is actually coming from, in the case of BERT, is coming from is encoder only stack. BERT is an encoder only stack. So now encoder part is done. Why bidirectional? Because bidirectional means the sentence is taken from both ways. I am a student, and the input is given from through the other side. I am a student means there are two sets of uh, LSTM units or similar attention unit that we have seen. Means the encoders is two well, parallel. Then this output is concatenated over, and so bidirectional means the input is given two ways. So that way it is bidirectional, and so we can see in the first A section here that sentence pair classification, any kind of classification. So per task can be done here, like whether they match or not. Okay, so if they match, then similar results can be shown to the text summarization. We talk about if text summarization kind of applications, and then um, like language models can be generated from here, and the other task is after language models is so similar to this. Sentence 1 is passed, sentence 2 is passed, and it is separated through this separator column. CLS means this is starting, and then it is given through time, like we were giving the RN and then the LSTMs, similar kind of application. But in the end, what we are doing here, we are getting a class level because it's a classification task. So we are generating a class level. Based on that, you can classify which category it belongs to. Now, in the similar way, single sentence classification tasks, SSTs, and then Ola, these are the data sets that are here. So similar fashion, single sentence classification can be done like which kind of suppose we are having some problem like identification of something, that this is similar things applications can be generated here. Question answering tasks, we have a project here at MoogleLabs that we are developing a question answering task here, where the challenge there is that the input given is in the Hungarian text is given to us. Now we have to train a transformer. If we get the enough data points, then we'll try to generate a transformer. Otherwise there are other multiple methods also. So and one we have one Hindi to Gujarati translation application here, and so similar kind of transformers are being used here as well. So we are using these transformers. Similar question answering task, since I remember, so it was already we are using this same transformer that is trained on a squad data set, which is actually Stanford question answering data set, which is a pretty good data set and giving us pretty satisfactory results for now, and we'll fine tune it also. So these models can be fine tuned also with your data. So these are pre-trained models. Since these are trained on all these, so these can be used for pre-trained models and can be used for multiple tasks. Like initially for transfer learning, then the final layers can be changed, and you can use it for whatever task you want to achieve. But you can always use these pre-trained models and various Hugging Face and other various libraries are there, which you can directly use, right? So but is here single sentence tagging task, then it is in the last single sentence tagging task, means it is like encodings, embeddings and all. uh, we can perform that task as well, right? So then, yeah. So so as I mentioned also, that such BERT system or transformers can be used for different kind of tasks. What we are ultimately doing, we are generating a vector which has actually some information. Using that information, we can perform, and by changing the last few layers, we can perform any kind of task. For example, sentiment analysis, we can generate the sentiment of the we can know the sentiment of the sentence, right? And then similar other applications are question answering, translations from one language to another language. These are translation, text summarization. We also have a project on text summarization, where the whole text chunks of accounts text is given to us, and then we have to generate some key takeaways from that whole text. Like one pager or two pager is given to us, and then we have to summarize it in a few lines. So that kind of text summarization is there, and we are using transformer as well there. Then text classification task, different kind of text classification can be performed. Named entity recognition. So named entity recognition is actually one of the one of the primary tasks for transformers and widely used task, because transformers are used for named entity recognition extensively today's work. Because after you have done some named entity recognition, you can apply these named entities to various multiple ways tasks where even transformers directly cannot be used. So you can use these entity after entity is extracted, you can use it for various applications. So it is one of the interesting application for transformers. Then there is a speech recognition, which is we already know, since language modeling, image captioning that I showed you an example also. So similar, these all are the applications for the transformers, and to explore the world is full of possibilities, and so you can have your own interest. You can generate your own application, and you can better understand what kind of application you can make using transformers, because there ultimately there is a sequence information which is converted to a vector, and then whether it is text, whether it is audio, whether it is a sequence of images like in a video, or any other sequence, wherever there is a sequence information, you can use transformers as well, because obvious reasons, right? So yeah, these are few resources that I have gathered in these information from, I have learned from, and you can also get benefited from these resources. So that will be all. Let me take a sip of water, and Minkle will take over.
Hello everyone, it's me again. Before we move to the question answer round, I would like to take a few minutes of your time to talk about our company MoogleLabs. Founded by seasoned IT professionals, we specialize as accelerators and developers in future technologies to enable digital transformation. We are established in Canada with a development center in India and Australia. Our experts have already helped several clients globally in improving their business operations using AI, ML, DevOps, blockchain, and data science. Through this webinar, we aim to help others know the power of the latest technology. And if you ever need an IT company that supports this technology, we would be happy to help you to decode innovation and improve your business efficiency. Now that's out of the way. Weber can take over from here and answer questions in the chat.
Thank you, Minkle. Okay, you haven't received any questions so far. I can allow mics if anyone wants to ask questions. So, where the data is stored for trained words in encoder stage. Data is stored for trained words. I didn't mean, I don't know what, but what I understand is you are asking what is stored. Actually, in the learning stage, all the data is passed through these models. And as I mentioned in the RNN, let me give you another look at this. So here, these are sigmoid units, 10H units, all these are associated with some weights. Then these weights are actually learned. When we pass through this, the word each vector, then these vectors are actually passed through this edge of these units, and then the model actually learns the weights. How? Through the back propagation, right? Through time. LSTMs learn through back propagation through time. And that process is actually quite complicated here to describe in a few words. So understand this, that they are trained through back propagation means there is a loss function, and loss function is actually optimized by giving multiple inputs, and then how much input is changing, how much output is actually to the predicted output, and there is a actual output. How predicted output is close to the, how much is close to the actual output. So that is learned. So actually we are learning weights here. Weights are updated. So that way we learn the information or the data. Difference between GPT and BERT. Okay, yeah. So GPTs are actually a special type of, they are also special kind of RNNs, sorry, transformers, where GPTs are generative pre-trained decoder only stacks. Like encoders are, transformers are basically encoder only stack. GPTs are decoder only stacks, and architecturally they are similar, but the task that they are performed in many of the tasks, GPTs after GPT-3, the GPTs are working pretty well. GPT have multiple versions now, GPT 1, 2, and 3, and the text size that GPTs are trained is quite bigger. They have used common web, common crawl data, and the but is also trained on common crawl data and a lot of textbook data, Wikipedia data, and the data that I also mentioned in the slides. But is trained on all these data, and so GPTs are also trained on the similar data. But the number of parameters that it is trained, GPT is quite large, 176 billion or so. So that way it is computationally, transformers are computationally effective, and so BERT and GPTs have, but in some instances BERT performs better than GPTs. There are few applications, and I cannot name right now, but there are few applications where BERT performs significantly well than GPTs. So yeah, both GPTs and BERTs are used. The one major difference is that GPTs are actually uh, also a state of the art, but is also state of the art, but is open source and free, so you can use easily. But can be you fully downloaded, can be downloaded and or used through APIs also. and the whole open code is also open source for BERT, so you can use directly. And the potential for BERT is, I think, since it is open source, so it has more potential in terms of applications. Thank you. So, any other questions?
If anyone need presentation, can drop your email in the chat box.
Yeah. Is there any limitations for transformers? Yeah, there are like not everything is perfect. So transformers also have limitations, like they are, yeah, for example, they are pretty big to work with. You cannot easily train them. They need fine tuning, so they need a lot of data. For example, they are sometimes trained on so much data already that if you have a small data set, then you cannot fine tune well on them. So the data requirement is there. Then the biggest challenge right now is resources that we need to train a transformer is quite high. Like you need DZX boxes of at least 4 to train a simple over the week, even over the weeks. If you are training over the weeks, then so transformers takes a lot of computational power, a lot of resources to train, and a lot of data also as well. So that's the primary limitation for now. But these are state of the art at present, so they are being extensively used. Thank you. Any other questions? You can drop your emails in the chat box if you want to have this. You can be allowed to for Mike if you want to ask anything. Improvisation. Okay. Improvisation in what sense? I didn't get that, but I understand if improvisation by means um, what they can generate. Like we humans have thoughts, right? So, for example, so in some instances, for suppose essay generation, and one of the examples that I have used in the recent past is they have transformer based code generation. So that code generation is already an API and is being used. So multiple platforms support that, and you can actually given as suppose you are only writing a function, and then if you start only writing few words or few even in the essay writing also, if you start writing few words, then it can generate a lot of texts. So improvisation in that sense, yes, they are possible because you will not find similar. They are generating new content also. So there was a challenge also, and it was found that for significant number of people were unable to detect whether it is AI generated text or it is human generated text. Human have written actual human generated. So in that way, improvisations. I think you mean what type of uh, input that they can give means how much creativity they can have. So in that terms, they are as good as humans for now, not exactly as humans. Obviously there are some boundary cases as well, but AI has its own limitations because after all these are machines, they do not have creativity. But in terms of some learning and repeat and generating something new, they have done pretty well. Even humans have failed to judge that whether it is machine generated or whether it is uh, human generated. So in that terms, yeah, they can do improvisations. Thank you, Prabhat. Very good question.
Okay, so the next session from Moogle Labs will be on Web 2.0 to Web 3.0. So please drop your email address in the chat and we will keep you posted about the latest events. Thank you so much, everyone.